In the last lecture, we were talking about the process of global routing. Now, you recall during global routing, we had tried to find out the roughly the sequence of regions through which each of the net has to flow or pass through. And we had also mentioned that subsequent to global routing, we have to take up the routing regions one at a time and to complete the routing in each of them. Now, this phase of completing the routing individually in each of the regions is called detailed routing. And in this class, we shall start our discussion on detailed routing. First, we shall be looking at what the problem is all about and what are the different kinds of, you can say, representations we have for tackling or handling this problem, and subsequently we shall be looking at the actual algorithms which people have proposed to solve this problem. Firstly, just about the problem, what is detailed routing? So, this I have mentioned. So, detailed routing consists of finding the actual geometric layout paths. So, you try to find out the actual path on the surface of the floor through which each net will be passing through. And obviously, an obvious constraint is that two different nets must not intersect on the same layer. Well, here a term called layer is coming. Now, layer is coming due to the fact that, well, in a typical VLSI chip, the interconnection is not done on a single layer. There are often several layers available to you, and you can complete the interconnection by laying out wires on one or more of those layers. Typically, at least two of those layers are metal layers and the other layer may be diffusion or polysilicon layer. So, on these layers you can complete the interconnection. So, obviously, on a single layer the wires of two different nets must not intersect each other, otherwise there will be short circuit obviously. And as we had said that for detailed routing, we consider one routing region at a time. So, the problem we are solving in an incremental fashion, and the ordering of the regions we had mentioned something about that. There is a ordering which is created and the regions are, you can say, routed or handled in that particular order. So, to look at this picture, this process of detailed routing starts after global routing, and after this detailed routing is done, so we have found out the layout of all the wires. Now, it is often the case that after placement the area you had kept aside for interconnection, well, area was too much, you really do not require all of that area. So, you will find if you look at a snapshot of the floor plan after routing is complete, you will feel that there are some areas where there is some empty space still. So, often after detailed routing a process called compaction is carried out. Compaction tries to squeeze the layout as a final optimization phase to reduce the area as much as possible. So, these algorithms of compaction we shall see later after we finish our discussion on detailed routing. So, global routing followed by detailed routing, this is a two stage routing process or method. Okay. Now, during the global routing stage, you recall once again that the overall routing area that is available on the chip is partitioned or divided into a set of rectangular regions. These rectangular regions are the individual routing regions which we typically call a channel or a switch box. Now, to interconnect each net, we will have to find out a sequence of such regions. For example, if I want to connect a point here to a point here, we will have to find out what are the different regions through which this net has to go through. Okay. There may be a sequence of such regions. Okay. Now, one thing to note is that when we are considering global routing, we are only talking about a tentative path. But suppose when we are completing detailed routing or when you are going about the process of detailed routing, suppose you have a scenario like this. You have a block out here, say B1, you have a block out here B2. So, this will be a routing region. If you look at this, this is a routing region. Now, on the other side there may be other routing. For example, there is another block B3 on this side. So, there will be a routing region like this also on the other side. Suppose we are considering the problem of completing the route in this region first. So, we will be trying to interconnect the points whatever they are. Now, it is not necessarily true that all of these interconnections will connect points of B1 to points of B2 only. There can be some nets which will connect B1 with some point of B3 also. So, those nets will possibly be routed like this. They will have to cross this region and enter the other region. Now, the point to note is that when we are starting the problem of routing this particular region, you look at this point where this wire is crossing the boundary. So, the exact location of this point is not fixed. This wire we can lay out on the first track, on the second track, on the third track. So, initially this terminal is called a floating terminal with respect to the second region. So, for the second region the location of this terminal is not fixed, but once this region, the routing of this is completed, the location of this point becomes fixed. So, now this becomes more like a fixed terminal with respect to this region. So, the concept of floating terminal and fixed terminals comes into the picture like this. So, what I have said is that all the nets which are crossing a given boundary, they are called floating terminals, because their exact locations are not fixed till you are completing the routing. So, once you have completed routing that particular region, these floating terminals, their exact locations will get fixed and they will now be termed as fixed terminals. For routing the subsequent regions, these will be considered as fixed terminals with fixed coordinates. Okay? Fine. So, the ordering of the channel is important due to this, because some of the floating terminals will become fixed terminals and will make the subsequent routing problems easier. Okay. If they are fixed, then the conventional channel routers can be used to route them. Okay. So, we had talked about this earlier also, but again let us look at a couple of examples related to the order of the routing regions. The first example, we are taking a slicing placement topology which can be divided by horizontal and vertical slices. Now, in this case we can route the nets in the order 1, 2 followed by 3. See, here our assumption is that we are using a channel router, because I mentioned earlier a channel router is easier to design and implement as compared to a switch box router. So, a channel router will be having terminals on top and bottom with a free space in between for interconnection. So, you look at 1 is a channel with pins on top or bottom, 2 is a channel with possibly some floating terminals on the right. So, once we route 1 and 2, these floating terminals will become fixed terminals. Then you can route this 3, because 3 now becomes a true channel, all the terminals are fixed. But you cannot do it the other way around, you cannot start with 3, because these terminals you do not know their location. Okay, so, you cannot start with 3, you will have to start with 1 and 2 and then you will have to handle 3. Yes.
But if we start with 3, then the same points can become floating terminals with 3.
No, the point is that the way the channel routing programs work, well, you can extend some pins to the right or left, but you cannot flexibly change the points on the top or bottom. So, if you had taken this region 3 first, then these points, their locations are not fixed. So, you cannot use any of the conventional channel routing algorithms to route this. Before that, you will have to fix these points. Okay. But if you have a non-slicing topology like this, a wheel, then you can see that the definition of channels is not that straightforward. Like in this example, for instance, well, this is a channel. If you divide this portion, there are pins here, and out here there will be floating terminals. Similarly, this small thing will be a channel, this will be a channel, and this also will be a channel. But if you look at the other regions, say for example, you think of this one, say this region, there will be some regions like this one where you can find that there are terminals on all 4 sides. Similarly, this, there are terminals on all 4 sides. There will be several regions which will be acting as switch boxes. So, if you have a non-slicing placement topology, and in another example we had taken earlier, the plus shaped junctions. So, for those situations you cannot avoid using a switch box router, because there will be some regions which will be inherently, there will be switch boxes, and you will have to use a switch box router which is more complex, as you will see. Okay? Fine.
What will be the order here, sir?
Well, here normally we will be completing the channels first, then the other switch boxes you can do in any order. Okay. So, just coming back to channels and switch boxes once again, well earlier we had categorized channels as horizontal and vertical, but well, you can just without loss of generality, you can consider all channels as horizontal, you can always rotate it by 90 degree and consider the other way around. So, a channel is a routing region which is having 2 parallel rows of fixed terminal on top and bottom, like this diagram shows. These are the 2 boundaries. There is a block, say B1 here, there is a block B2 here. These are the terminals which need to be interconnected. This is a possible interconnection. So, this space in between is kept aside for interconnection, there are no obstacles out there. So, a channel is an obstruction less region which is used for routing, and a switch box looks like this, where pins may be located on all 4 sides of the boundary, and this is a typical interconnection. This interconnection can be done on a single layer or multiple layers. So, we will see the different approaches later. Before we talk about the routing algorithms and the problem of detailed routing in general, first let us look at some of the issues involved. Well, when we talk about routing, there are a number of different things we need to look at. First, of course, is the number of terminals corresponding to the nets. Now, it is true in general that most of the nets are 2 terminal nets, but of course, there are nets like clock, power, some kind of a signal which is going to many different places, where the number of terminals can be large. Typically, clock and the power nets, due to their very high cardinality with respect to the number of terminals, they are handled in a different way. So, whatever algorithms we are discussing now, they do not apply to clock and power routing, they will be handled differently, right. But many routing algorithm will see, in fact, most of the channel routing algorithm will be discussing, they either handle 2 terminal nets or a multi-terminal net you can break up into 2 terminal ones, but some of them can handle multi-terminals also. So, if necessary, the multi-terminal nets can be decomposed into several 2 terminal nets. So, this may be necessary, this is not required for all algorithms, but for some it may be necessary. Second issue is regarding net width. Well, we had mentioned in the last class that for high performance circuits, some of the signal lines may be wider than the others, but we are not considering that issue right now. Well, even without those constraints for high performance designs, normally the power and the ground nets have greater width as compared to signal nets. Greater width because they will have to carry more current, but the thing is that greater width is fine, but the width of the power and ground nets need not be uniform all throughout the chips. The point where it enters the chip, it is the widest out there, and from there it is getting distributed. So, each branch of distribution will be thinner than the main trunk, and from there again they are getting distributed. So, wires are getting even thinner. So, the different segments of the route will be having different widths depending on the estimated amount of current it is expected to carry, right. Fine. There are some other issues. Well, there is something called via connections. Well, we had mentioned that we have typically more than one layers available for interconnection. Suppose we have layer 1 and layer 2. There is a wire, a segment of the wire which is running on layer 1 and a segment of the same wire net running on layer 2. So, in order to complete the connection, we have to make a connection between these 2 points. So, what we are saying is that if a portion of the net is running on layer 1 and another portion of the net is running on layer 2, I am showing in my different colors, then at the junction there has to be some kind of a connection made. This is typically done in VLSI fabrication technology by drilling a hole and putting some kind of metallization to make the connection. This is called a via connection. Via connections are essential if you are using a multi-layer router, but reducing the number of via connection is also desirable, because more the number of via connection, more will be the area taken and less will be the reliability. So, as you connect across layers, your reliability and the performance also slightly degrades. And regarding the vias, there can be 2 kinds. One is the regular types of via connection where you only connect between adjacent layers, but you can have a stacked via also where 2 layers are getting connected where there is more than one layer in between. So, it is a very deep interconnection. So, stacked via are more difficult to implement in terms of the fabrication technology, and it takes more area to fabricate, right. So, these are the 2 different kinds of via. So, suppose you want to connect a metal line with the diffusion of the polysilicon line, then you may have to drill down deeper to get access to the layer beneath, down below. So, that will be a stacked via. Well, there is another issue regarding the boundary type. Boundary type is the boundaries of the blocks. Well, typically we have regular boundary types where the borders are all straight lines, but in general it can be lines which are oriented at any arbitrary angles. There are some CAD tools which allow boundaries at arbitrary angles other than 90 degrees, vertical and horizontal. Number of layers is an issue. Before you do the routing, you must know that how many layers are available to you. Modern day fabrication technology typically allows at least 5 layers. Well, out of these 5, typically 2 of them are left aside for power, ground and clock. So, you have 2 or 3 layers available to you. Net types, you can categorize the net types. Some of the nets are critical. Power, ground, clock are absolutely critical. In addition, there can be some signal nets also, which you can categorize in the critical category. But the non-critical nets are the other ones where, well, you have some flexibility there. You can find a longer route if the need arises for that. So, the slight increase in delay is not important for those. Okay. And there is another issue, this is regarding the routing models. Now, most of the algorithm that we will be discussing, they will be based on the so called grid based model. Grid based model says that you have an imaginary matrix of, you can say, lines, horizontal and vertical. So, all the interconnecting lines will pass along the junction of these rows and columns. So, you cannot have a line from any arbitrary location, from this middle you cannot have a line like this. So, the lines will be all of the same width and they will have to pass just exactly along the boundaries. This is the grid based model. So, actually for signal routing we typically use the grid based model. Then when we talk about a channel, we typically talk about the number of rows available, the number of columns. So, implicitly we are assuming the grid model. But when we are say routing power, so we are not interested in the exact places from where the lines are routed, it can be anywhere and the width can be different also, because typically there is a different metal layer which is available to us for routing the power. So, we have complete flexibility out there. This is the so called gridless model. So, it need not follow the boundaries of the grids and the widths also may be different, right. Okay. Yes.
Grid models we have followed like the Lee algorithm, the headlock.
The Lee's algorithm is different. There the grid, that the interpretation of grid was different. That the whole layout area was divided up into grid cells, where each grid cell was, you can say, the smallest entity you can talk of. Suppose a terminal. So, a terminal will belong to one grid cell.
So, like in that algorithm, when we lay down a wire,
yes,
we consider it to be an obstacle for the another wire to be laid down.
Yes, yes.
But so that wire can be in some other layer, because we can have here still that space will be open for us.
Yeah, you are saying that in the Lee's algorithm, the way the algorithm we had talked about, we had considered that everything was laid out on a single layer, but you can easily extend Lee's algorithm in a two dimensional plane. We can consider that there are two planes, one on top of the other, that corresponds to the two different layers. So, you can extend Lee's algorithm to two layer model also. So, that is really not an issue, but usually Lee's algorithm is used when, so means as you can say, as the last resort, when you have laid out most of the nets using some other method, some of the nets you are unable to find a path, then you use the Lee's algorithm or the line search algorithm to find out a path. Now, if there are multiple layers available, you will have to extend that basic Lee's model.
So, that model actually for a single layer.
Yes, yes. That model is for a single layer. Okay. So, when you talk about multi-layer routing, there are broadly two approaches. First says that there is no restriction as such. This is called unreserved layer model. This unreserved layer model says that suppose you have two layers of routing. So, you can lay out wires in any fashion on the two layers. Of course, if it is a gridded model, you will have to lay it in synchronism with the grid rows and columns, but other than that there are no restrictions. This is the unreserved layer model. But in the reserved layer model, it says something like this, that well, in layer 1 you can only lay horizontal tracks, on layer 2 you can only lay vertical tracks. Well, if you make some restrictions like this, your algorithms for routing becomes much easier. Moreover, say in adjacent layers, if we have two parallel tracks running over a long distance, the capacitance will be more and the delay of the signals and the noise will be more. But since they are crossing across adjacent layers, the effect of noise and the interlayer capacitance is also much less. So, typically we use the reserved layer model unless the problem is simple enough to be routed in a single layer. Reserved layer model says that, well, you have some restriction as per the horizontal and vertical tracks. So, if it is a 2-layer routing problem, then we normally go for HV or VH. H means in layer 1 only horizontal tracks, in layer 2 vertical tracks, or the reverse. If it is a 3-layer routing problem, you can go for VHV or HVH, right. So, some simple examples. Say this shows a typical illustration for the HVH model. Well, I am showing this by color. This is say the first layer 1, layer 1 is H, layer 2 is this is layer 2, layer 2 is vertical, and say this is layer 3. Layer 1 or layer 3 will be horizontal, layer 2 will be vertical. So, this is a typical example. Similarly, VHV model. So, there are 2 layers which will carry vertical lines, say this is one, this is the other, and you can have one horizontal line. This example shows an unreserved layer model where we have 3 layers, but there is no restriction. You can have one layer which can carry both horizontal and vertical line segments. You can have one which can carry both horizontal and vertical line segments. Similarly, the 3rd layer can be like this. Typically, when you are routing the power and ground, that usually follows the unreserved layer model, because in power and ground, since you are trying to carry high current, you do not want the via connections, because via connections are the sources of additional impedances. There can be voltage drops there also. Now, here one thing you observe here, that every time you move from one layer to the another, for example, here, these are all via connections. So, the number of via connections is also an issue. Some of the algorithms you will see, they ignore the via connections, but there are some algorithms which also take this into account and they try to minimize that. Okay, fine. So, now let us come to the channel routing problem and see how people have tried to approach this. So, as I have mentioned that in channel routing you have a rectangular region called the channel, which is left for interconnections, and that region does not have any obstructions. And these channel routing algorithms which we will talk about, they are unlike the grid routing algorithms like Lee's, where we route the nets one at a time, and once we route a net, it becomes an obstacle for future nets. So, it is not like that. We are trying to find out a global solution using an algorithm. So, we are considering all the nets at a time. Channel routing is important because most of the ASICs we design nowadays, they use channel router because most of them use this standard cell design style, and standard cells implicitly they use channels. The algorithms for channel routing are efficient, and you will see that they are also not very difficult to implement. And the most important thing is that if you have a channel with flexible channel width, then 100% routing completion is guaranteed. Well, by channel width, you can mean both ways, either the channel is wider or the channel height is more. So, you can adjust the channel size in any direction you want to, but if you have this flexibility, you can guarantee 100% completion. well, for channels there are some terminologies. We define something called tracks in the channel. These are the horizontal rows which are available for routing. Trunk is a horizontal wire segment corresponding to a particular net which is laid out on some track. Branch is the other way around. Branches are the vertical wire segments. They connect the trunks to the terminals. And of course, via is a connection between a branch and a trunk. I am taking an example. Say I have an example out here. This is an example channel. This is the upper boundary, this is the lower boundary. These are the terminals. Terminals are typically arranged in synchronism with the columns of the grid. Each terminal is labeled with a number. This number indicates the net. 1, 1, 1 means these three belong to the same net and they have to be interconnected. Similarly, 2, 3, so on. 0 means no connection. So, the channel specification you can express very efficiently by two arrays, top and bottom. Top will contain these numbers 1, 2, 0, 2, 3, bottom 3, 3, 1, 1, 0. So, the kth element of these arrays will indicate the terminal in the kth column of the channel of this problem, I mean. Okay. Now, this gives one possible solution to this channel routing problem. So, let me show this by color. This is a 2-layer routing model, say HV. One layer is horizontal and the other layer carries the vertical connections. Okay. So, now according to the definitions which you had given earlier, these are the tracks. This is one track, this is the second track, this is the third track. These are tracks. There are 3 tracks on which you can lay out the horizontal segments of nets. Okay. These are the trunks, segments of the net. For example, for net 1, here to here there is a horizontal segment which has been laid out on track number 2, suppose 1, 2, 3. This is a trunk. Similarly, for net number 3, this is the trunk. For net number 2, this is the trunk. The vertical segments are the branches. They connect a trunk to a terminal, Sometimes this example does not show you, a branch can also connect one trunk to another trunk. For example, you can have a connection like this also. There a branch will connect this trunk with this trunk. You will see later that it becomes necessary sometimes to break a particular net in more than one tracks. Of course, this example does not require that. A particular net can be completely laid in a single track in terms of the horizontal trunk, right. Okay. So, first let us go into the problem formulation. The channel is defined by a rectangular region just as mentioned with 2 rows of terminal on top and bottom. Each terminal is assigned a number between 0 and n, where n is the number of nets. Terminal having the same label I, they belong to the same net. 0 means no connection. The net list is represented by 2 arrays as I mentioned, top and bottom. The kth element of the array represent the labels on the kth column of the channel, top and bottom. Okay. So, this is the input to the problem. Now, the channel router will be taking that input specification and will try to assign the horizontal segments of the nets to tracks, assign vertical segments to connect either horizontal segments of the same net in different tracks, just as I mentioned, zigzag kind of a thing, or the terminals to the horizontal segments. So, the channel router will make these assignments to complete the routing. The objective is obvious, the channel height should be minimized, means number of tracks you require, that has to be minimized. This is the primary goal. Of course, we have not talked about via connections as yet, we will see it later, that how we can minimize via also. But while doing it, there are some constraints that must not be violated. These are called horizontal and vertical constraints. Let us see what these constraints are. So, any channel router must not violate these constraints. Now, these constraints are fairly obvious. Say a horizontal constraint says, suppose I have a net 1, say with 1 out here and 1 out here, and a net 2 with 2 here and 2 here. Well, if you look at the horizontal spans of the two nets, the net 1 spans from here to here, net 2 spans from here to here. So, there is an overlap between the spans. Now, since they overlap, you cannot lay out these two nets on a single track. You will require minimum 2 tracks for these. So, if there is a horizontal constraint like this, then the two nets cannot be laid on the same track. So, in general, if there are p number of nets which mutually they have horizontal constraints with each other, then minimum p number of tracks are required for routing. This will give you a lower bound to the number of tracks required. Okay. Similarly, you can have something called vertical constraints. Vertical constraint says that suppose you have a channel with a terminal labeled 1 out here and exactly down below you have a terminal labeled 2. This says that if you lay out the horizontal segment of net 1 say out here, then the corresponding horizontal segment of net 2 must be below this, it cannot be above this. If you try to do above this, there will be a short circuit here, it has to be something like this. There exists a column such that the terminal on top belong to one net and the terminal j on bottom belong to other net. So, at least on this column net I must be assigned a track above that for j, because if you try to do it the other way around, in terms of the branches there will be a short circuit. Okay. These are the constraints. Now, these constraints are expressed in the form of a graph. First, for the horizontal constraint, let us take an example. This is a more elaborate example of a channel with the points noted. Now, a horizontal constraint graph is a graph where the that there is a horizontal constraint between them. Now, drawing the HCG is very easy. You just observe the horizontal span of the different nets. Say for 1, this is the span, this is for net 1. Net 2, it starts with here and ends here. Net 2, this span is this. Net 3, it starts here and ends here. So, the entire span. Net 4 from here to here. Net 5 from here to here. These are the horizontal spans. Now, if you look at the horizontal spans, you see that other than 4 and 5, the others are all mutually conflicting. So, the corresponding graph is an almost complete graph without this edge between 4 and 5. Okay. Now, in this graph you can find out the maximum sized click. Now, click is a complete graph, a complete subgraph. Now, in this graph of 5 vertices, you can find out that the maximum click you can have is a subgraph of 4 vertices. If you take this subgraph, this is a complete graph. This will mean that any solution to this problem will require minimum 4 tracks, because there are 4 nets which are mutually conflicting horizontally. This is the lower bound. Okay. Fine. Similarly, you can have a vertical constraint graph, VCG. VCG is a directed graph, because here you keep track of who is above whom. Here 1 is above 3 in column 1, so there is an edge from 1 to 3. 2 is above 1, so from 2 to 1 there is an edge. 2 is above 5, 2 to 5. 1 is above 3, 1 to 3. 1 is above 4 and 4 is above 2. Rest are no connections, zeros are no connections. So, from a given specification you can have a vertical constraint graph. Vertical constraint graph will give you some information regarding in which order you will have to do the routing, or you will have to assign the, you can say, segments of the nets to tracks. This we will see subsequently. But one thing let me tell you, that the problem case is when the VCG contains a cycle, as this example also contains a directed cycle. So, if a VCG contains a cycle, this is a problem case, you will have to have some kind of a zigzag kind of a connection, we will see later. Okay. So, we first look at the different 2-layer channel routing algorithms, because they are the most widely explored. There are multi-layer, 3-layer channel routing algorithms which have been proposed, but they are mere extensions to this. So, first we will have to understand very nicely or very clearly that the main or the important 2-layer channel routing algorithms. 2-layer means H and V, on one layer horizontal tracks, other layer vertical tracks. The first important class of algorithms, they are based on a very simple concept called left edge algorithm. The basic version, an extension of it with vertical constraints, and something called a dogleg router. Then there are some algorithms which are based on something called constraint graph. There are a couple of algorithms there. Then greedy channel router and hierarchical channel router. This we shall be looking at. So, to start with, we look at the basic left edge algorithm and its extension. The basic left edge algorithm is very simple in concept. Well, the basic left edge algorithm says that you have only 2 terminal nets, but you will see later that this assumption is not mandatory, this can be relaxed. This is a relaxable assumption. So, you need not restrict yourself only to 2 terminal nets, you can have multi-terminal nets also. Well, the basic version assumes that there are no vertical constraints, which means that a pin belonging to one net cannot be above a pin belonging to some other net. This means that if you have a signal pin labeled 1 here, the one below it must be labeled 0. Similarly, if you have a pin labeled 2 here, the one above that should be labeled 0. This is of course a very restrictive assumption. This is the basic version of the algorithm, but we will see later that we can just relax that also. This is a 2-layer model, horizontal, vertical. Dog legs are not allowed. Well, I do not know why they call it dog leg. I have never seen a dog with a leg like this. Say a net like this is called a dog leg, where the horizontal segment is broken into more than one track. This kind of a connection is called a dogleg. There are two horizontal tracks on which the total horizontal segment is assigned. Now, with these assumptions you will never need a dogleg. The basic steps are very simple. This says that for each net you look at the horizontal spans and you sort the net according to the x coordinate of the leftmost terminal. The net with the first terminal on the left in terms of the horizontal span, you keep it first. So, in that order you sort them. Route the nets one by one according to this order and you place the net in the first track. You can place them scanning from the top to bottom. For a particular net which you are trying to route, scan the tracks from top to bottom and assign it to the first track that can accommodate it. So, the algorithm is fairly trivial. You look at the horizontal spans of the net, the one which is coming leftmost with respect to the left terminal, you assign it to the first track, take the next one, you see that whether it can be accommodated on the first track, if not, put it on the second track, take the third one, you again scan from the top, you find out the first track where you can put it, you put it there. In that way you go on putting them. Now, in the absence of these constraints, it can be shown that this produces a minimum track solution for obvious reasons. You cannot do any better, you can just if you look at the algorithm, though it works. Now, as I had mentioned that this no vertical constraint assumption is too restrictive. So, first let us try to avoid this assumption to make it slightly more general. So, the way we can do this is very simple. There can be vertical constraints, which means that the VCG is not a null graph, there are edges in the graph. Now, VCG will dictate that which node should be routed first. You take a simple example, suppose net 1, just below it net 2. So, with respect to the VCG, from 1 there is an edge to 2. Now, in terms of assignment to the tracks, you know that well net 1 must be placed on the track first, net 2 must be placed on a track below it. So, now what I say is that I would be following or honoring the ordering in the VCG. Well, I will be sorting the nets as earlier, but I will be picking up a net for routing provided in the corresponding graph there are no incoming edges in the corresponding node. If the graph is like this, then 2 is not a candidate. I cannot take 2 for routing before 1, I will have to take 1 first. First I will route 1, then I will remove this 1 from the graph. In the residual graph again I will do the same thing. I will only pick up nodes which do not have edges coming from some other nodes. Okay. So, now the algorithm will be like this, that we can select a net for routing if the x coordinate of the leftmost terminal is the least. This is like the basic algorithm, and secondly there is no edge incident on the vertex corresponding to the net in the VCG. So, if you follow this, then you can get a solution. But of course, after the routing of that particular net is completed, you will have to delete that vertex from the graph, that vertex and the associated edges. Okay, we have an example to illustrate this. Let us take this example. This is a slightly more complex example with nets 1, 2, 3, well 4, 5, 6, 7, 8, there are 8 nets. Okay. Now, in terms of the vertical constraints, you see 1 is above 3, so 1, 2, 3, 2 is above 3. 5 is above 6 and 7 is above 8. Well, there is a vertex 4 also, but 4 does not have an edge with anybody else. 4 0 4 0, there is no vertical constraint. So, if you look at the leftmost boundaries, if we try to sort, say leftmost boundary is net 1. So, first we will have net 1, then 2, then 1 we have taken 3, then 4, 5 and 6 they start from the same column. So, 5 6 both in any order we can have this, then 7 8 again starts from the same column. So, this is the sorted order. Now, we would be laying out nets in this order subject to the constraints in this graph. First, let us take 1. Well, we can take 1 because this node 1 does not have any incoming edges. So, we take 1, this is the span of 1, we complete this assignment. You assign the horizontal segment in track 1, remove this node from the graph, then take 2. You assign, there is a horizontal constraint between 1 and 2. So, you assign it to the next available track, remove it from the graph. So, now 3 is also candidate. Now, in this list 3 comes next, you assign 3 to the next available. 3 cannot be put on row 1 or row 2, it has to be put on row 3, track number 3, remove 3. Then comes 4, you can put in the first track without any, there is no horizontal conflict between 1 and 4. I have not shown the HCG, you will also have to have that. So, 4 can be laid out on track 1, 4 is done. Then 5, no constraint, 5 you cannot put on track 1, it has to be put on track 2, remove this. So, now 6 is also ready, you take 6 cannot be put on track 1 or track 2, this has to be put on track 3, 6 is done. Then 7 can be put on track 1, this is the horizontal segment span, 7 is done. Then 8, well 8 starts from here and it has a horizontal conflict with 7, 5 and 6. So, it has to be put on the 4th track, this is the final solution. So, basically the left edge algorithm, it assigns a net to a track, just the horizontal lines. Now, vertical lines you can complete after that. The way these are assigned, there will be no conflict in assigning the vertical lines. Yes.
You have 1 2 2 1. How do you do
Okay,
that?
okay. I was just about to say that. You are saying that you have a problem where 1 2 2 1. So, here you are saying that in the VCG there is a cycle. You have a situation like this in the vertical constraint graph. Now, if you have a cycle, you must have a dogleg. There are two ways you can do it. Either you see, you need an additional free column. If the free column is in the middle, then you will have a dogleg like this, or if you have a free column on one side of it, suppose there is a free column out here, okay. So, you complete or on the other side. So, there what you do, you complete this routing, then net 2 you will be going to this column, then again you will have to come back on another row. So, you will be needing additional, so 3 tracks anyway, you will be needing 3 tracks in both cases. So, the idea is that if you have a cycle in the VCG, you will have to break the horizontal segment of at least one net into more than one track. Okay. So, this doglegging algorithm we will be discussing in detail in our next lecture. Thank you.